Most books on material handling and rigging will give you this figure that chokers are 75% efficient. And reality is a little more complex than that. You can make a choker more efficient, better than 75%, and you can make on the job site the choker less efficient just by doing this. Let me show you. Here I've got this nylon web sling here. Well, if you're making a choker on a nylon web sling, you loop it around the load, and this is going to be your main line there, and this one's looped around the load. You can make a choker weaker by hammering down this intersection point of the choker, this loop here, closer to the load, or stepping on it. Now, depending on how wet your web sling is, or how dirty it is, or how much friction is in it, you can hammer it down to a certain degree. And because there's two sides to everything, you can improve the efficiency of the choker when it is looped around the load, and you lift this loop a little bit up on the main line that's holding the load. Now, I realized instantly that chokers tend to have particularly nylon or polyester web sling chokers have a tendency to balance themselves. So they will, even if you raise it up, it will kind of sink back down to a point where it balances its natural balance point, and it is going to be close to that 75%-ish efficiency. But chains are different. On a chain, here's the lid of my cookie tray. Just imagine this is a pipe that's long and is being lifted. You can set your choker to make it look like so. You can set your choker to make it look like even more relaxed, like so. And you can move this grab hook all the way down here to make your choker look like just something like that, to make it really, really tight. If you do that, you weaken the choker, or not entirely weaken, you reduce its safe workload by way below the 75 percentile. Its efficiency can be reduced to 50 or 30% if you do this to a choker, especially with chains. And of course, if you make the choker's legs longer here a little bit, make the intersection with the grab hook higher up on the main line, then you improve the choker's efficiency to be better than 75%. It can be 85, 90, 95% efficient. So you can lift heavier loads and you don't have to reduce the choker's efficiency by that much. And I'll show you how it's done with a little bit of geometry here. First off, here's my calculator. First off, take a look at this nylon web sling. The manufacturer did not stick to the 75% figure that's quoted by the textbooks, and there's nothing wrong with that. It works perfectly fine because you can do this up and down on the choker. See, its vertical safe workload is 3,200 pounds, and on choker it's 2,500. But 2,500 is not 75% of 3,200. I'll show you what number. 2,500 divided by 3,200. See, 2,500 is 78% of 3,200. So they went with 78 instead of 75. If they wanted to go with 75, they should have done 3,200 times 0.75. They should have printed 2,400 on the choker. 2,400, 2,500. I'm not saying those are close enough. I'm saying within the choker's capability and adjustability, those are both realistic figures. What I'm saying is the 75% figure that textbooks give you, it's not set in stone. It isn't that it applies to all chokers in all times, in all places, in all working conditions. No. you can make a choker worse and weaker, and you can improve its efficiency likewise. So I'm going to do a little bit of geometry with this one. You see that these legs on the choker wrap a circle around partially. If the choker is shortened and its efficiency is lessened, then the legs are shorter and they wrap the circle more. Take a look at what's on the sheet of paper here. Let me just get some more white surface here just for white balance, and maybe do this with the camera. There. Okay. This way, and let me just do it this way. Getting there. Okay, that seems to work. Alright, I have this big circle here. How you can look at it in terms of geometry is fairly straightforward. This line here and this line here represents a basket configuration. In a basket hitch, the load is suspended like so. So that's what those lines are. These lines here, this blue one here, it's blue, you can kinda see it there. This bigger triangle starting from here is a choker that is having longer legs here and is touching the load there. This line, in terms of math, is a tangent line, tangent to the circle. The meaning of the word tangent is that it's touching the circle at one point. If I connect these 2 points of tangency, okay, because these are the 2 legs, working legs on the choker, if I connect these 2 legs on the choker, I get here a straight line. This is the chord in the circle, that particular chord that belongs to this particular choker situation. On this one, we can actually calculate the working load limit reduction just like anywhere else by taking the headroom or its vertical height from where the chord intersect the plumb line, the vertical, and from this point here where the choker's loop forms. Okay, so you take a measurement from here to here. You can eyeball you can eyeball it on the job site. You can see where this intersection point is roughly, where the chain starts going away from the load, and you can just take a vertical measurement on the outside here, but you have to start it at the point of tangency and just eyeball it up there. I know it's not gonna be an engineering super accurate calculation, but it's gonna be an approximate enough. So there's your headroom, and for length you just measure this length of the choker's length here from the point of tangency to the point of intersection there, and when you divide height by length, you're gonna have an efficiency number out of it. I don't have a height or the length number here. I have something else. This blue triangle here, this working load triangle, I get closer a little bit, just give me a little slack here, and let's say that that's a 30-degree angle and that's a 60-degree angle, because it kind of looks like it's approximate enough. It's a 30, 60, 90 triangle, okay? And that 60-degree angle is what we are determining with the height and the length. And when I enter sine 60 into the calculator, I get that figure, 86.6% efficiency for the choker in this particular configuration. And this 86.6% is right away better than the 75% quoted number. So the working load limit of this one, whatever figure the manufacturer gives you on vertical, would not need to be reduced down to 2500. It can be a little higher, so you can lift heavier loads in a pinch safely if you manipulate your choker to be more efficient and make this intersection point closer to the hook, if indeed, or in fact you move this intersection point further down and you wrap your load better, it would tighten the chain around the load a little better and it would secure it better. However, it worsens the choker's efficiency. You look at this red triangle here. In this red triangle, the line of tangency is running here, and its point of tangency is there. Same on the other side of it. I just extended the tangent line just a hair. I know that the chain is not gonna stick away from your load, or your web sling is not gonna stick away from the load, so well, I'm just pointing out some geometry detail with this. Again, for this red triangle, you have a chord here. The chord intersects the plumb line there, and you have a height here for this load, for this smaller new load triangle. You can also estimate this height if you look at it, and estimate where the point of tangency is from the outside, and just eyeball it and take a measurement next to the load somewhere here. Also take into consideration the length again, divide the height by length. In this case, I'm just gonna eyeball neither the height nor the length. I'm gonna eyeball these angles, and how about, it looks like a close enough to 45, 90 degree triangle, right? It's not exactly, but just give me a little slack here. 45, 90. Let's enter into the calculator the angle instead of the height and the length, and let's go sine 45 equals 0.7. So that means it's a 70. Okay, there's one more digit there, so I can round it up to 71% efficiency if the load is wrapped more. See, now we are below the 75% quoted efficiency. So it's the 75% is somewhere higher here, and the 78 that the manufacturer here printed on this one would be somewhere here. Now most nylon web slings will balance themselves between 70 and 85, somewhere there, where the choker naturally forms. But again the chains don't do that. You're gonna have to set the chain for your choker, and in an absolutely unreasonable move, you can make this choker even tighter. Say, how about lower this intersection point there, and in that case I'm just gonna pencil in a tangent line there that forms a point of tangency somewhere around there. It's just free-handed in, okay? And that means that it's got a matching line there, another point of tangency there, and the chord would be formed there. So I have this new height going from there to there only, a new lesser height, and that's the length on the load triangle from there to there. I'm not going to calculate with the height, but I could estimate it from here on the outside of the load from the point of tangency, and just eyeball it up here and just take a look at it. Instead of working with the height and the length, I'm going to estimate this angle here and say, how about 30 degrees? It looks like a 30, 60, 90 triangle. Let's go with 30 degrees, see what happens if I enter the same sine 30 equals 0.5. In this super tight configuration, the choker now is only 50% efficient, a lot less than the quoted 75. And if you hammer down this intersection point on the choker, particularly on a nylon web sling or on even on a wire rope web sling, and the rigger stands on it and pushes it down out of some kind of miscalculated zeal, it's not going to work well with the choker's working load limit. It's going to be drastically reduced to 30%. Okay, so that's all I have to say about that subject.